Matthew Gomez from Sandia, an alumnus of this program. He's a principal member of the technical staff in Radiation and Fusion Experiments Department, the Pulse Power Sciences Center, Center 1600 as it's sometimes called, at Sandia. As I mentioned, an alumnus. He studies inertial confinement fusion and high-intensity science with the Z machine, which you can see in the picture. I guess you got to see yesterday, or not yesterday, Tuesday. He was a SSGF recipient from 2007 to 2011, where when he earned his PhD from the University of Michigan. And in 2014, he was already clearly having an impact because he received a DOE NNSA Defense Programs Award of Excellence. His numerous publications and this work that he's going to describe today has appeared in the popular literature, or more popular literature in different places. So, Matt?
So, you guys had the opportunity to tour the Z machine, and I'm going to talk to you about some experiments that I've been doing with the ICF program at the Z machine. But before I go into that, one of the things that Krell asked me to talk about was sort of how I got from a graduate student to the position I have at Sandia right now. So this is the timeline of graduate school for me. I started at the University of Michigan in 2005. I was working with Ron Gilgenbach in Plasma Pulse Power and Microwave Lab in the Nuclear Engineering Department. I was working on contact resistance in wire array Z-pinches and working on transmission lines and developing and working on new pulse power systems such as the linear transformer driver. I applied for the program in 2006, the first year it was open. I didn't get it. I applied again in 2007, and I did get it that year. And so this is actually a picture, and I think Forrest and I might be the only people here from this, but here's me, here's Forrest, and we have the rest of the fellows. This is from the 2008 meeting in Washington, D.C. So this was after the summer after my first year in the fellowship program. And so, like most of you have already completed, but some of you are still looking at practicum experiences, I completed mine at Sandia in Albuquerque in 2009. I thought it was a really great opportunity, something that I probably wouldn't have done otherwise. Turns out that my advisor's, one of his first graduate students from the 80s happened to be a manager at Sandia, and he was looking for somebody to do some pulse power diagnostic work at Sandia. It was kind of out of my comfort zone because I had never worked with visible spectroscopy before, but it was something that I thought I could probably learn, and I at least had the background in pulse power, so I felt like it was a reasonable stretch. So in the summer of 2009, I went out to Sandia and I set up the streaked visible spectroscopy system. A number of people have used it since then for all sorts of things. Actually, Rick, when he was coming out as a student from Harvard, I think, was using that system for some of his research. And so it was a really great opportunity, and the thing that was exciting about it was I got to know all the people that worked at Sandia on the Z machine. And it was a new group of people. I got integrated into the system, and I really got along with my practicum coordinator. And because I liked him so much, and we had a requirement for an external member of our dissertation committee at the University of Michigan, I actually asked him to be on my committee, which meant he knew when I was getting close to graduating, and he let me know that they had a position that was open in his department, in the Radiation and Fusion Experiments department. And so when I defended, I had already applied and gotten an offer to work at Sandia as a staff member, which was really exciting. So you have sometimes opportunities to come in as postdocs and do some really interesting work. Since I was already integrated into the system, I knew all the people at Z, it was a pretty easy transition for me to just jump right in as a staff scientist. And I was the PI, I was already on the schedule as a PI for the Z machine on an experimental campaign before I had officially accepted the job. And about, I think, within 2 months of starting in March of 2011 was the first shot series I had on Z. And I've done, I think, at this point, right around 75 shots, about 25 different experimental campaigns over the last 6 years. And I've dabbled a little bit lately into some of the more managerial side of things. I was an acting manager last summer, and I've stayed on in sort of a position of trying to coordinate some of our programmatic efforts. It's been a really great environment. I love the Z machine. I really enjoy working at Sandia. And so I guess I would look to any of the students who haven't done their practicums yet or who are thinking about a second practicum and just say, consider this as a great opportunity to meet somebody who may be your future employer, some of the people who you may be working with. It's a really nice opportunity that not everybody gets in grad school. And those connections really can help you move forward in your career. And so now I'll just move on to the actual scientific portion of the talk. You guys got to see the Z machine 2 days ago. I was on a tour with a couple of you. So I won't belabor this too much, but just to remind you, it's a 33-meter diameter machine. It stores energy in capacitor banks that go around the outside of the system. It's about 100 cubic meters worth of storage volume. And then you're taking all of that and you're firing all of that energy into the center here, which is about 1/10 of a cubic centimeter is where your target. So you're compressing the energy that you've stored in space by about 9 orders of magnitude. And at the same time, you're also compressing it in time. So you're storing this energy over several minutes. It's about 20 megajoules of energy. So that's sort of tens of kilowatts of power that you're putting into the machine. But the energy is being delivered to the load in 100 to maybe 1,000 nanoseconds. So that means you're compressing this energy in time by about 9 orders of magnitude as well. So this is a huge change in the energy density, the power energy density. And the peak electrical power on the Z machine that's being delivered is about 80 terawatts. So to put that in perspective, the average total global electricity usage is something like 15 terawatts. So we're only doing this for a very, very short period of time, but it's an incredible amount of power. And as you guys saw, you start off with something that looks nice and clean and this pristine experiment, and you load in these other diagnostics, and you can see they look a little bit beat up already, and that's because when you fire the experiment, the target itself, some portions vaporize, some turn into plasma, some just liquefy or blow apart in shrapnel. But everything's destroyed, including sometimes some of the diagnostic equipment. That's because you have 3 megajoules of energy that's being delivered to this central region, which is being done over such a short period of time. It's equivalent to a few sticks of dynamite, but those sticks of dynamite are going off instantaneously by comparison. So on Z, we're basically limited to about 1 shot a day, and that's because every day you can see the hand of somebody who's in here, a technologist, who has to go in and clean up all the stuff that's in here, remove it, refurbish the transmission lines, reinstall it, install the new hardware, and then we shoot at the end of the day. And so that, I kind of wanted to give you an idea of, I'm going to talk about ICF experiments because that's primarily what I've been working on for the last year or two. But the Z machine is really dedicated to more than just ICF. It's the full stockpile stewardship, the stewardship science effort. So this is a breakdown of our 2017, the current year, allocation on the shot machine, or on the Z machine for shot days. We start off with 250 working days in the year, and for this year we expect to get about 160 shots. And you can see that the working days are broken up. There's about a quarter of the time, a little bit over it for ICF, and similarly a little bit more than a quarter for dynamic material physics. And then radiation effects and other higher energy density physics, that's the other big stewardship science area that we work in. We're dedicating 7% of our time to fundamental science this year, which is a relatively large number. And then there's a small number of shots that are considered facility shots to exercise things that like after we do a rebuild or something like that, you have to verify that the machine's working properly. And this year we happen to have a large block of maintenance. This is sort of a strange year. We have to rebuild the insulator stack on Z about every 3 years, and we did that earlier this year. It takes about 20 days, 20 working days. We also happen to be rebuilding our transmission line refurbishment region of the machine, which takes another about 14 days. So one of those we only do every 3 years. The other one we do about every decade or so. They just happen to coincide in the same year, so it looks like there's a lot of maintenance this year. But this is, the 160 shots that we're getting is fairly typical. We can do up to about 200 in a year with a lot less maintenance. So I'm really going to focus on the ICF efforts that I've been involved in at Sandia from this point on. So I just want to kind of give you guys a quick review of traditional ICF. So you start off with this sphere and it contains deuterium and tritium. Sometimes there's some gas with an ice shell, but the main point is that you have a material that can undergo thermonuclear fusion. You then implode the sphere by your method of choice. You want to compress the radius by a factor of 30, which is changing the volume by 27,000. This is incredibly difficult to do in a symmetric way, but if you do, you can get a really impressive energy state. So you're sending a series of shocks into the center of this target, and you're using that to heat that center, creating a hot spot. If you zoom in on that region, you can see that there is a low density hot spot at the center that's surrounded by a cooler, dense shell. And so the idea is that that hot spot is going to undergo fusion reactions. It's going to generate charged particles that are going to travel outward, and they're going to deposit their energy into the cooler, dense cooler, dense shell that is surrounding it. When that energy gets deposited, that area locally heats up and can undergo fusion reactions, and then you can get this propagation outward. But that only happens if you have a favorable power balance. So in ICF, you have to be able to balance the amount of energy that you're depositing with the amount of energy you're losing through radiation, the amount of energy you're losing through electron thermal conduction and ion thermal conduction. This is a very simple way to look at it, but essentially for traditional ICF, you can plot out your fuel temperature and your areal density, which is just a measurement of the density of the fuel times the distance you have to travel through it. And you can get an idea about where this power balance occurs. So the black line shown here is where this equation is balanced. Everything in the gray region means you're going to get a runaway thermonuclear reaction, and everything in the white region means you're going to just fizzle. And so there's a couple interesting points. One, there's a minimum temperature that you need to operate at, and that's because your fusion reactions are going to be balanced by your Bremsstrahlung radiation losses. So you have to be at least about 4.5 kilovolts in order to get something out of this. The other thing that's interesting to note is that there's a minimum areal density. And that's because when you're creating these charged particles, you need them to be depositing their energy relatively locally. Otherwise, you're not going to be able to heat up that spot enough to get the chain reaction you want. Now, it's really hard to go up in areal density. It's also very hard to go up in temperature. So ideally, you would want to operate right in this little corner here. That's the easiest spot to access. But is there something that we can do to make that spot a little bit easier to get to? So if we apply a magnetic field, we can start to relax some of these conditions. So here I've applied a 0.1 megagauss centimeter magnetic field. So I'll just say that when I say magnetic field, what I'm talking about is magnetic field integrated over a spatial dimension. And so that's why it'll always be in terms of a magnetic field and like megagauss centimeters. So the interesting thing here is we've applied this magnetic field, and we open up this region of parameter space now that previously wasn't accessible. So it's a little bit easier to get to this point than it is to get to this point. At this magnetic field, we're effectively suppressing our electron thermal conduction, but we're not doing much about the ions, and we're doing nothing about the Bremsstrahlung radiation. So that's why you will always have this 4.5 keV, no matter how high the magnetic field gets. So if you keep increasing the magnetic field, you get to a point where now, at 0.3 megagauss centimeters, the Larmor radius of the alphas that you're generating in the fusion reaction is roughly the same as the radius of your fuel. And so what that means is that you're going to start trapping a good amount of that energy, and you're basically opening up more of this space. And here you're also tending to magnetize your ions, so you're also able to neglect those thermal conduction losses. So as you go just a little bit higher in magnetic field, where your Larmor radius is now noticeably smaller than the actual fuel, you start to open up a much larger region of parameter space. And if you keep going, you're now relying more heavily on the magnetic field to trap the particles than you are on the actual areal density to deposit the energy. You still need the density there so that energy gets deposited, but the particles will be trapped for a long enough time just by the magnetic fields. And eventually you get to a point where you start to saturate. So when your Larmor radius is about half of that of the fuel radius, then you're effectively saturated, and now you can operate sort of at almost any areal density with roughly the same temperature. And so our goal in magneto-inertial fusion is to try and operate somewhere more in this region rather than up here. The neat thing about this is, although I'm talking to you about experiments that happen on the Z machine, this is not a unique concept to what's being done on Z. So you guys may have seen, whoever's been around for a little while may have seen the National Ignition Facility at Lawrence Livermore. This is probably the most common fusion concept, that ICF concept you might be familiar with. It's a gold can that you shine a bunch of lasers into. You create X-rays inside that can, which then ablate a capsule and cause it to implode and create fusion reactions. At the Omega laser facility, they're pursuing something called laser direct drive, where you remove the gold can and you just shine the lasers directly onto the target itself. So it's a little bit more efficient, but you have to deal with symmetry issues more often in that case. At Z, we're working on magnetic direct drive, where we apply the current directly to the target and cause it to implode. This is really neat because Z is a very efficient machine compared to some of the lasers. But one of the differences is that on the Z machine, the rise time of the current pulse is 100 nanoseconds or so, whereas in laser facilities, the implosions are happening on 10 nanosecond timescales. So what that means is that at Z, we have to use some of these tricks like magneto-inertial fusion to get something to work, whereas at Livermore on the National Ignition Facility, you don't need the magnetic field, but it can still be used to help you. So I'll talk to you about magnetized linear inertial fusion, or MagLIF. This is a concept that we've been working on. It was invented about 10 years ago. We did our first experiments about 4 years ago, and we've been really excited with how things have gone since then. The concept relies on basically 3 principles. One, you'll apply an axial magnetic field to your target. In the second, you'll use a laser to heat that fuel. And in the third, you use the current from the Z machine to compress your target, which compresses up and increases the temperature of your fuel and increases your magnetic field. So sort of breaking that down, you're applying this axial magnetic field, again, to limit your radial charged particle transport. So you want to keep the hot fuel from reaching the cold walls. So you start off with a metal cylinder that contains about 1 milligram per centimeter cubed of gas. And it's about 1 centimeter tall and about 0.5 centimeter in diameter. You then use Helmholtz-like coils that sit above and below the target to apply an axial magnetic field to the target. And you have to do that over a relatively long time scale because this thing is made out of metal and there's a whole bunch of metal conductors surrounding it that are coupling the current to the target. And so you have to allow the magnetic field to diffuse through those conductors. So you then use a laser. In this case, we're using a green laser because that's what we have available in the Z beamlet laser. It's a terawatt class laser. It's a few nanosecond, few kilojoule pulse. And we use that to heat the fuel. Now, in order to enter the fuel, it has to pass through a window, a thin plastic window. And it turns out that that plastic window actually tends to eat up a lot of our laser energy. So we use about half of our laser energy burning through that window, and the rest of it gets deposited into the fuel. But we're still able to heat the fuel to about 100 eV. And then again, remember that we're applying this magnetic field in the first stage so that now over this tens to 100 nanosecond long implosion, that energy isn't lost all to the walls. And so in the last stage, we're applying roughly 17 mega-amps from the Z machine to the outside of this target, causing it to implode. So we're generating about a 3,000 Tesla azimuthal magnetic field around the target. You get a radially inward Lorentz force from that. And the target's imploded at about 70 kilometers a second. So by comparison, in most ICF concepts, the implosions are happening at something like a factor of 5 higher velocity. And that's important because in order to get the shocks that are heating those targets and to get everything to the states that you're trying to get to, with the hot spot at the center and the cool, dense fuel surrounding it, you have to be imploding at these much higher velocities. So we really are reliant on this laser heating stage to get us to a few hundred eV, and then we can only really compress up semi-adiabatically to a few kilovolts from that. At the same time, our magnetic field that was initially about 10 Tesla is being amplified through magnetic flux compression to roughly 1,000 to 10,000 Tesla. And so at Sandia, one of the goals in setting up this concept was we thought it sounded really interesting and intriguing from experiments, but from simulations, but we wanted to do experiments for each of the stages to make sure we understood how we could actually achieve the conditions that were required. So this is the target here at the center. We fire a current up through this region to the target and back down. We have these coils that sit above and below the target, providing an axial magnetic field. There are diagnostics embedded in these coils that we use to understand the magnetic field that's being applied. So that's the first stage. The second stage is the laser heating. So we do some standalone experiments where we fire a laser into the target. We don't implode the Z machine, and we just look at X-rays that are generated by the target, by the gas with dopants in it inside of the target. And that can help us understand about how hot we're getting the target and where that energy is being deposited. And then we also did a series of experiments where we used this laser as a radiography source. So we create X-rays and then take backlit pictures of the implosion. So we can see that initially the target has roughly this inner and outer radius. And you can see that these are snapshots over several different experiments, but you can see it imploding towards the axis. Now, when we combine all of this together, we end up with a stagnation column that's a very high aspect ratio, which means it's very tall and very narrow. And it emits a burst of thermonuclear neutrons. So again, for scale, this is the initial target diameter, and this is the region that we're getting our emission from. So if you zoom in on that, you can see that it's about 8 millimeters tall, and it's only about 100 microns wide. And given that our initial target diameter is about 4.5 millimeters, we're talking about convergence ratios that are very high. So this is not necessarily ideal. This is something that we're working on right now to try and increase the back pressure so that we can decrease our convergence ratios. We look at the neutrons that are emitted with a series of different diagnostics, and from those we understand that the primary neutron yield is relatively isotropic, and the spectra are as well. And the neutron production that we observe follows the trend we would expect for the measured ion temperatures. So that gives us some confidence this is a thermonuclear reaction. And so we've measured primary neutron yields up to 410 to the 12th, and that's in deuterium on deuterium, which is important because there's a much lower cross-section for deuterium on deuterium at these temperatures than there is for deuterium on tritium. So there is about a factor of between 50 and 100 scaling between the two. And so one of the things that we established is that if we just implode our target and we include the fuel in it, but we don't add any magnetic field or any laser, we essentially get roughly the background that we would get if there was no fuel in the target. When we apply a magnetic field, we see a small increase in the total amount of neutron production, maybe a factor of a couple. But when we apply all three components together, we see something like a 2 to 3 order of magnitude increase over the background. And so because everybody in here may not be super familiar with these reactions, I just wanted to reiterate, primarily we're using deuterium on deuterium, which means we're producing a neutron at 2.45 MeV, shown here. But at the same time, there's an equal probability branch of this reaction that'll produce a triton at about 1 MeV. Now, because there's a very high probability of reaction between that triton and any other deuterons that are located in the target, of which there are still many, you can get this secondary neutron reaction producing about a 12 to 17 MeV neutron. And so we measure both of these, and in particular, the high energy neutron is important because that can tell us something about our magnetization at stagnation. So this is roughly our geometry in a cartoon form. It's relatively tall and thin. Our height is much larger than our radius. If we consider a case with no magnetic field, and then think about the tritons that are created in a fusion reaction here, you can have a triton that either travels radially out of the target, and there's going to be, the vast majority are going to do that. It's not going to interact with very much in the way of any other deuterons because it's a small distance. And so you're going to have a very small probability of an interaction before it escapes. Now, if the triton happens to travel axially, then it has a much larger path length it's passing through. So it's much more likely to have an additional reaction, producing a secondary fusion reaction. And so that's kind of interesting because geometrically there's this effect where you tend to favor neutrons that are axially oriented when you have no magnetic field or a very low magnetic field. Now, if you look at this with a neutron time of flight spectrometer, and you generate a triton here that produces a neutron here, if it's directed in the radial direction, the neutron, and it gets detected, it'll be at roughly the nominal energy. But if it happens to be directed in the same direction as the triton was, and it's detected, it'll be shifted up in energy by several MeV. And if it happens to be going in the opposite direction that the triton was going, then it'll be shifted down in energy by several MeV. And so what that means is that if you have a detector that sits to the side and a detector that sits above the target, and you sample over many different reactions, your axial detector will have this double-peaked structure, and then your radial detector will have this single-peak structure at the nominal energy. Now, it's important to note that because we have no magnetic field here, we're not really expecting many reactions to occur, but this is the shape that you would see in simulation space, at least. Now, if you apply a magnetic field to this, you change this substantially. So the triton that was traveling axially still can react in the same way it could before because your axial magnetic field doesn't change its trajectory. But if your triton is traveling in the radial direction, it's being bent by that magnetic field, and it's basically trapped inside of the fuel, which means it has an equally high probability for interaction. And so now it doesn't really matter what direction your tritons are born in. They'll all have an equally high probability of reacting, which means you should see a much more isotropic spectrum for the secondary neutrons. And so in simulation space, what that looks like is at 0.25 megagauss centimeters, you have this double peak structure for the axial. As you come up to 0.4, you have something where the axial peaks start to get closer together, and at about 0.7, everything's uniform. So if you remember back to the initial plot I showed, or one of the initial plots I showed, 0.6 megagauss centimeters is roughly where you start to see this effect saturate. So experimentally, what we observed is this double-peaked structure, but it's not a completely separated double-peak structure. So we know that our stagnation magnetic field radius product is somewhere around 0.3 to 0.4 megagauss centimeters, which is starting to get into that region where we're depositing a lot of our energy. And so that was one of the really exciting things, and we feel like we've demonstrated a number of the key aspects of magneto-inertial fusion at Sandia on the Z machine so far. We've measured ion temperatures, magnetic fields, and plasma densities that are all kind of within a factor of 2 or so of the range that we're trying to get to on Z. And we've demonstrated a DT equivalent yield of about 1 kilojoule. So again, I told you we only use deuterium on Z. We're working towards including tritium on some experiments. It's moving forward at a slow but steady progress. But we've achieved about 1 kilojoule in these experiments. Our end goal is to get to somewhere between 10 and 100 kilojoules on Z. We think we can do that, but in order to get there, we need to increase our initial fuel density, our laser energy that's being deposited into the target, the applied magnetic field, and the current that's driving it all simultaneously. So this is a big challenge. So something that we've been focused on for about the last year or so after we fleshed out the beginnings of this project are trying to improve each of these cases. So one of the things that we changed about our laser very recently, just in January of this year, we did our first tests with a phase plate. So we originally had a laser profile, laser spot that looked something like this. It was unconditioned because it wasn't necessary for what the laser was being used for. But for this experiment, we got a lot of feedback from the other labs. We've been working with people at LLE and at the NIF to try and understand laser propagation. And one of the things that they suggested was to use a phase plate to try and smooth the beam. So we switched over and added a phase plate in, and we also changed our laser pulse shape from the black trace here to the red trace, where we effectively kept the same amount of energy being sent to the target, but we changed the intensity of it. And by changing the intensity of the laser by about an order of magnitude, we dramatically reduced the stimulated Brouillon scattering that we observed in these experiments, which is pretty important because that's an indication of laser plasma instabilities. And one of the things that came out of this was about a factor of 2 increase in our total neutron output by making this change. And this is just changing the laser by itself. We want to couple this with some of the other changes that we've also tried. So we've also demonstrated that we can increase our current by changing the transmission line design. So we started off with something that looked like this with, again, you're passing the current up through this long feed to get to your target because you have magnetic field coils sitting above and below it. We've recently done a test with a much larger magnetic field coil that sits above the target. When we switch over to this new configuration, we can achieve the same magnetic fields, but we can increase the current by about 3 mega-amps, which is pretty substantial. We were also looking into modifying our magnetic field coil technology. We typically operate with this 10 Tesla magnetic field coil. We've done a couple experiments with these 15 and 20 Tesla coils, just initial testing. We haven't really integrated them into a full experiment yet. And we even have this 25 to 30 Tesla coil design that exists, but it limits our diagnostic access. So we have to try and get a balance between being able to understand everything that's going on in the experiment versus trying to push up the performance. And we are working on other additional new coil technologies, but they really push the limits of what's possible. And we have worked a little bit with the National High Magnetic Field Laboratory at Los Alamos on this. So really, to take advantage of all these things, we have to increase everything together. Looking at where we're at right now, this is about 10 Tesla initial magnetic field, half to a kilojoule of laser energy, and 16 to 18 mega-amps. We're trying to achieve over the next year or so an increase of magnetic field to 15 to 20, laser energy to 1 to 2 kilojoules, and 19 to 20 mega-amps. So I'm leading a series of experiments actually next week on Z to take the first step towards this. We're going to do another series of these experiments in October or November to try and push it further towards this goal. By 2020, we'd like to increase all these parameters further, and we feel that's kind of where we need to be to get into the 10 to 100 kilojoule neutron yield range, DT equivalent range. So we have these new coils that we're testing that we're hoping to use in the fall that'll get us to 18 to 26 Tesla with these higher currents and with the higher magnetic fields. I'm sorry, and with the higher laser energy. And we're also testing some new laser configurations in September that hopefully will feed into those fall experiments. So you can see this is something that's really relatively new and it's dynamically changing. We're adding a lot of components together. So it's a pretty exciting area of research. But of course, we always have to be looking to the future, even if we're still trying to understand what's going on right now. We've been developing at Sandia for some time the architecture for a new pulse power facility that would be even larger than the Z facility in terms of current delivery. And so that's based on this technology called linear transformer drivers, which if you remember all the way back to the beginning of my talk, that was actually what I was working on in grad school before I got involved in all the work at Sandia. So that was really exciting for me that this thing has kind of come full circle. We're looking at basically a new facility that would be a 50 mega-amp driver as opposed to sort of a 15 to 25 mega-amp, which is where we're at right now. So it's a factor of 2 to 3 larger, and it fits in the exact same footprint as the Z machine because it's a more efficient technology for delivering current. So our goal over the next 3 or 4 years is really to demonstrate that we understand what's going on in this MagLIF concept that I've been talking to you about, and that we can scale things by increasing some of these input parameters. In our in the near-term future, 5 years from now or so, we're really interested in trying to develop what the path forward looks like to a 1 to 10 megajoule nuclear yield, thermonuclear yield. And we would really be looking to try and design this facility to couple with the experiments that we think will produce that type of yield, so that in the late 2020s we can get to the final designs of the machine, and hopefully around 2030, when many of you will be 5 years or so into your graduate or your postgraduate career, we'll be working on construction of a new machine, and you can come to Sandia and do some really interesting experiments. And I should say, although I've, again, said this from a very ICF-centric standpoint, the dynamic materials program, the radiation effects program, all the other high energy density physics programs will benefit from a future machine like this as well. So this is something that we're trying to make a concerted effort so that all of the stewardship science campaigns can benefit from whatever the new machine looks like. And with that, I'll take any questions you have.